We learned about the equilibrium constant and calculating that with respect to molarities of components, reactants, and products. So Kc is the equilibrium constant with respect to concentrations. Here we're looking at molarity. For a reaction that occurs in the gas state, the partial pressure of the gas is proportional to its concentration. And so we can also use partial pressures to calculate an equilibrium constant. This is called Kp, equilibrium constant with respect to pressure. Here the pressure is always given in atmospheres. So again, the products raised to the power of their coefficients divided by the reactants. Any questions about that? So Kc and Kp are not necessarily the same number, but they are related to each other. And we're going to look at how that comes about. So the partial pressure of a gas in atmospheres obviously is not the same as its concentration and molarity, but it is related. And we can find that relationship from the ideal gas law. Bivnert. So I'm trying to get N over V, because N is moles and V is volume in liters. So N over V is molarity. So I'm going to divide this side by V and divide that side by V, and these guys cancel out. And then I'm going to divide by RT over here and RT over there. And these guys cancel out. So then we have N over V is equal to P over RT. We don't typically think of gases as having a molarity, but they do. And it's related to their partial pressure. It's not the same, though. Any questions? So we can say that the concentration of gas A is equal to the partial pressure of A divided by RT. So we're going to figure out the relationship between Kc and Kp, and we're just going to use our generic equation again. So first we'll start out by writing the equation for Kc with the concentrations. C raised to the C power, D raised to the D power, divided by A to the A power, and B to the B power. Well, up here, this says the concentration of any of these gases is equal to its partial pressure over RT, so we could sub that in. I'm going to go down a line because otherwise we're going to run into that equation. Down a little bit further. So that would be the partial pressure of C over RT to the C. So this would be times the pressure, but we have 1 over RT to the C power. Well, fractions get messy, so we could also write that as RT T to the negative C power. Is everybody okay with that? When you change the sign of the exponent, you invert it. So by going from a positive C to a negative C, I upside down it, and now I've just got RT. So then what I've got over here is RT to the negative C times RT to the negative D divided by RT to the negative A and RT to the negative B times PC to the C, PD to the D, PA to the A, and PB to the B. So I separated the partial pressures from the ideal gas constant and the temperatures. Any questions? I'm not going to make you derive this ever. I just want you to see where it comes from. Well, this guy right here, that is Kp, right? I'm going to get rid of this guy because I need some space. There's different ways to think of it. So Kc is equal to, when you multiply things raised to a power, like if you have x squared times x cubed, you add the exponents. So this is the same as x to the 5th power. So the numerator here, that is the same as RT to the negative C minus D. And in the bottom, we've got RT, minus A minus B. And then that's times Kp. This part is Kp, okay? Just trying to, it's like, what's the best way to explain it? So if we have RT divided by something, then instead of adding the exponents, we're going to subtract the exponents. So this RT over that RT is just RT raised to this minus that. So I'm just going to save some space. Okay, it's not going to let me do that. Fine. So we could say that that's equal to RT to the A plus B minus C plus D. If I distribute this, oh, that's not a pointer. So if I multiply these, I get positives, and then I'm going to pull the negative out of this guy. So we've got this. What we want is we want Kp equals something. So I'm going to divide both sides by this mess. When I divide by the mess, I change the signs. So we're going to end up with RT to the C plus D minus A plus B times Kc. Well, that's not a very nice looking equation. So instead of the C, D, A, B stuff, we just call that delta N. So delta N is equal to, oh yeah, it's up here. C plus D, so it's these coefficients minus the reactant coefficients. It's products minus reactants. It's the difference in number of moles of gas. Yeah.
How did KP and KC switch?
KP and KC switched because I changed the signs on this exponent. Yeah. Like I said, I'm not going to make you derive this. But what I did kind of in my head is I divided both sides by this, and then I didn't like that in the bottom. Yeah, because this is not equal to KP, this is equal to KC. That's a little confusing. Let's see if we can make that look a little better. This whole thing. So KC is equal to this. So I'm dividing both sides by this. This cancels out on that side. And then I end up with KC divided by that. Instead of dividing by it, I'm just going to change the signs on the exponents. Okay? So that's where I got this from. And then that's really messy. And so we're just going to call that delta N. And this doesn't need to be there anymore. So delta N is moles of gas products minus moles of gas reactants. Again, we're keeping that delta tradition of final minus initial, or products minus reactants, right? Any questions? So that looks a lot nicer than all the scribbling. But that's where it came from. So delta N is the difference between the number of moles in the products and the reactants. And if we have the same moles of gas before and after, what does delta N end up being? 0. If delta N is 0, then RT to the 0 is 1, and Kc is equal to Kp if it's same number of moles, because then all those RTs cancel out. If it doesn't, then there's going to be RTs left. And by combining it like this, we don't have to go through and do all the RTs. Consider the following reaction. What's the value of Kp at this temperature? So Kp equals RT to the delta N times Kc, or, switched around. So we need to find out the difference in moles of gases. How many moles of gas products? 2. And how many moles of gas reactants? 2. So delta N is 0, which means that Kp equals Kc, which is 6.2 times 10 to the 2. That's one of those that seems too easy. It's not always like that, but it can be. So I don't know why they don't give us one that's actually different, but they didn't in the book, they didn't do that. Any questions about that? The hardest thing for me to remember as a student was, what is delta N? And we're talking about gases and partial pressures. We're looking at moles of gas products minus moles of gas reactants. It can be a positive number or a negative number. Do you have a question?
The temperature, we do change it to kelvins.
Temperature has to be in kelvins, yes. Yep. Any questions? Okay. Well, we've been doing these equilibrium constants, but we haven't written any units on them. We did have units for the rate constants, right? Here, the equilibrium constant doesn't have any units. And it's a little tricky the way they work this out. But when we're looking at the concentrations of those reactants and products, we're not actually looking at the molarity of this. We're looking at it in reference to exactly 1. So when we see, when we see 0.10 molar A, I guess I don't need the brackets because what we are actually putting in the thing is 0.10 molar over 1 molar, and the units cancel out. When we're looking at pressures, we're actually looking at the pressure of it in atmospheres divided by exactly 1 atmosphere. So that might be, 2.0 atmospheres in relationship to 1 atmosphere. And so then now we've just got 2. So what that does is it makes all the units go away. Some of you like me are like, well, no, we can't just say no units, right? So this is the rationale. These are all ratios, and that makes the units go away. For those of you that don't care about that, as long as we just use molarity for the concentrations and atmospheres for the partial pressures, we're just not doing units on equilibrium constant expressions. Because they end up being totally meaningless anyway. It has to do with the number of products and reactants and what their coefficients are raised to, and you've just got molarities to some power. And so it doesn't mean anything anyway. Any questions?
You said they were ratios?
Yeah. So, yeah, so let's go back to something. No, maybe we don't. Whoops. You know what, we're coming up on a section where we actually calculate an equilibrium constant, and please remind me and I'll show you there. Otherwise, I'm going to just get lost in my slides here. So here again, we have that generic equation. What are the circumstances that would make Kp and Kc be equal to each other? Moles of gas on each side being the same, right? Does it matter if the reaction's reversible? No. When we're doing an equilibrium, we're always looking at reversible reactions. Does it matter if the equilibrium constant is small? No. Well, what does this mean? This means the total moles of gas is equal to the total moles of reactant gases, so delta N is 0. So that's when they're the same. Any questions?